Hello, good afternoon. My name is Cesar, and today I'm going to present ScaleCheck, which is not really about erasure coding. It's an approach for discovering scalability issues in large distributed systems. This is joint work with Risa, Juan, Jeffrey, Shanlu, and my advisor, Hariadi, from the University of Chicago, Tanakorn from Samsung Research America, and Wei-Chu Chuang from Cloudera. Okay. So over the last decade, there are many different types of bugs that have been looked into by the community, like performance, concurrency, configuration, or security. However, after studying many bugs, we feel that there is a new class of problem that haven't been looked into carefully. The reports for these problems look like these ones. So for example, in Cassandra, a customer says, hey, I have this problem, but I only see it when I deploy 100 nodes or 1,000 nodes or more than 500 nodes, and so on. And not only in Cassandra, other systems like HDFS, HBase, or Riak also exhibit these kinds of issues. So what are these scalability bugs? Well, here, when you deploy a small cluster size, the symptom does not appear. But as you scale, you suddenly see a symptom show up. And that is the definition, latent bugs who only appear at large scale, but not necessarily in small, medium scale deployments. Let me give you an example using Cassandra. So here we have a ring of n nodes, and each node maintains a set of key ranges. And let's say we want to remove one node. What happens is that all of the other nodes have to broadcast that departure to figure out how the key ranges have to be rebalanced across all the live nodes. So when the number of nodes is small, everything is fine. But when the number of nodes is large, give me a second. Oh, sorry. But when the number of nodes is large, you see nodes declare dead, because gossips are late. So why are these messages late? The algorithm to rebalance the ring that runs on every node is O(n cubed, where n is the size of the cluster. And that means that there is a triple nested loop iterating scale-dependent data structures. That computation is very CPU intensive, and when it's long, what happens is that gossips come late, and they are not processing time. So in a large cluster, node 8 believes node B is dead. But a moment later, the gossip of B arrives. Then A believes B is alive. So these nodes are sometimes alive and sometimes dead, and so on. In Cassandra, this is what developers call flapping. And when the cluster is flapping, the whole cluster is unstable. So now, we reproduce this problem. And here, in the x-axis is the number of nodes, and in the y-axis is the total number of flappings times 1,000. And we can see that for small cluster sizes, like 32, 64, or 128 nodes, we don't really see the problem. But when we deploy 256, we do see it. Now, this is not just a one-time thing. We found a series of problems that cause the same symptom, but happen in different workloads. So how do developers currently find these scalability issues? The state of the art is real scale testing. This is deploying a large number of machines. So paraphrasing Andrew Wang, an Apache Hadoop PMC member, testing at 1,000 node scale is the most effective way of finding bugs. But it's difficult, expensive, and it takes a lot of expertise. Because of that cost, solo contribution is almost impossible, and developers heavily rely on large companies to do some scale testing. So finding scalability bugs in a single machine will be extremely useful. So these are the realities that motivate our work and raise two questions. Sorry. First, what are the root causes of scalability bugs? And second, can we do large-scale testing easily, like in one machine? And motivated by these two questions, we introduce ScaleCheck, an approach for discovering scalability bugs, and democratizing large-scale testing. Going back to our first question, we studied thousands of bug reports from several systems like Cassandra and HDFS, and from those, we collected hundreds of scalability bugs. And for some of them, we found one frequent root cause: scale-dependent loops. Loops that iterate over data structures whose size is scale-dependent. For example, on the number of nodes or on the number of files. And for this, we built the first component of ScaleCheck, SFIND, a generic program analysis tool that automatically finds scale-dependent data structures by checking their in-memory growth tendency over small-scale experiments. Then, for our second question, can we do large-scale testing in a single machine? And to do that, it turns out that there are many, many challenges we need to tackle. Like, for example, memory overhead, context switching, CPU contention, network overhead, and sometimes even bad modularity, because sometimes proper testing is impossible due to bad design. And to address these challenges, we built the second component of ScaleCheck, STest, a framework that implements 3 colocation techniques, namely single process cluster, or SPC, which is a runtime environment to simulate a cluster in a single process, global event-driven architecture, or GEDA, that provides global handlers for per-node events, and processing illusion, or PIL, to address multi-node CPU contention. And with these 3 techniques, our framework allows developers to perform large-scale testing in a single machine with little to no source code modification. With these tools, we automatically analyze 15 different versions of 4 popular systems, namely Riak, Cassandra, HDFS, and Voldemort, and scale-tested 18 different protocols, focusing on frequently under-tested operational ones like rebalance or bootstrap or decommission. With that, we accurately reproduced 10 known bugs and found 4 new ones. And we did all of this in a single commodity machine. So after this brief introduction, I will describe our approaches, SFIND and STest, and I will close with evaluations and conclusions. So let's go with SFIND. So now we have a frequent root cause, scale-dependent loops, traversing scale-dependent data structures. So if we find the data structures, we find the loops. But if we take a look at any distributed systems these days, how can we find those in a code base that has more than 100K lines of code, hundreds of source files? And looking at the fields from those files, there are thousands of maps, lists, queues, and other data structures. We know we can find them manually, for example, by looking at the comments. This is a comment from Cassandra for a map that holds 1 entry per peer, for example. This one is from Riak, for another map holding the relationship between partitions and nodes. And this one is from HDFS, a map that holds blocks per data node. But in such large code bases, we don't want to rely on comments. So now the question is, how can we automatically find these data structures? So let me show you what we can do. With Cassandra again as an example. Let's say that we have a single node cluster, and if we observe the heap of that node using, for example, JVMTI and reflection for Java, there is a list called peers that stores the current members of the cluster. So let's call this step 1, and on the bottom, let's keep track of the growth tendency of that list. This is in the x-axis the size, in the y-axis the size, and in the x-axis the step. So we are going to keep track of the size at each step. Now, if we add one more node and observe the heap again, the same list has 2 elements, and the growth tendency is modified as well. And if we do the same n times, we will see the modification in the growth tendency of that list too. So now, if instead of just looking at one data structure, we do this for all of them, keeping track of the growth tendency of each one, we will find that some data structures have a tendency to grow when the size of the cluster grows. And those are what we call scale-dependent data structures. And with this method, we can now automatically find them. But we want to find them all or most of them. And for that, only adding nodes is not enough. We need to try out different access of scales, like adding files, for example, or partitions, or tables, or columns, or et cetera. So with this, we find over 26 data structures in total, assuming Cassandra and HDFS. But that is not enough by itself. We also need to try out different workloads, like snapshotting or decommissioning in Cassandra again, because some data structures only grow when this kind of workloads trigger. And with this, we found a total of 18 data structures, assuming both systems. So now that we have our data structures, we can use data flow to map them to loops and create call graphs for every method. So for example, here we have two Cassandra methods, apply state locally and send to endpoints. And we can now analyze these two call graphs. So what is our goal here? Well, developing test cases takes time. So we want to prioritize what to test. So we're prioritizing what do we look for. First, the nesting between loops to get an idea of the complexity in terms of scale-dependent data structures. So following this, you can see that send to endpoints should have the same priority than apply state locally. In this case, the same complexity. But this nesting is not by itself enough. There are other important factors, such as I/O, as in this case, scale-dependent I/O, or blocking operations, as waiting for some lock or for some future result. In this case, again, scale-dependent. So S-finds also looks for these bottlenecks operation and in the body of each method. And with that, we can help developers prioritize the potentially harmful methods over the ones that might look complex, but in reality, they are not. Let's continue with our framework as test. So now we have analyzed our code base, and we found scalability bug candidates, and we prioritize them, the ones that we think are bottleneck prone, like here, apply state locally, right? So now we can write a test case for this method. And when we run it, we want it to behave as if we were testing at a real scale. But we want to use just a single machine. And as I told you, there are many, many challenges when doing this. So now let's describe our journey to overcome these problems and create our framework. So this is the first thing we try, our baseline approach. We call it naive packing. And the way this looks like is like this. We have as many processes as we can running in a single machine. And when we say process or node, we mean one system's instance. So with something like this, we could only reach a colocation factor of about 50 nodes, meaning we cannot run more than 50 nodes on a single machine. And this prohibits single machine scale testing in an easy way, right? So this happens mainly because of two reasons. First, there is an overhead associated with the runtime environment of each node. And that will clearly limit the number of nodes we can deploy in a single machine. But before hitting that bottleneck, what we noticed is that process context switching was already causing some inaccuracy. And by inaccuracy, I mean event lateness, as in something that is supposed to happen every second, for example, sending a message, now it's happening every 2 seconds. And this accuracy is very important for us, because if we don't have it, we won't be able to observe the symptom as if we were testing at a real scale. So with that in mind, we started building our framework. And to get rid of process context switching, we create a single process cluster, or SPC for short. And the way this looks like, we have a process with many groups of threads, each one representing one node. And surprisingly, this was really hard to achieve. Many systems are not really designed to run in this way. Some of them lack of modularity. They heavily make use of bad design patterns, for example, like singletons, that make this kind of configuration almost impossible in a black box fashion. So the first thing we did here is to implement per-node isolation. For example, on Java-based systems, we can do this with class loader isolation. In that kind of setup, now those bad design patterns are overridden automatically, and each node resources remain isolated. So now we can deploy them without being worried on how the system was designed. After that, we were having trouble with context switching because we had too many threads in a single process. So we simplified internode communication. So now, instead of using socket, each node has a queue to receive messages, and the sender just places a message in that queue, which will eventually be consumed by the owner. So with this approach, we reach about 120 nodes. That is a single process. But after that, we will still facing some inaccuracy, mainly because, albeit we reduce the number of processes and the number of threads, we still need to reduce the number of threads per service. And let me show you what I mean. If we look inside a node, we will find a frequent design pattern. Each node is built as a set of services, and each service is basically a worker pool processing events from a queue. So the way this looks like now in our single process is that we have one copy of each one of these services per node, so the amount of threads we have is too large. And we were looking for approaches to reduce that. So our next approach is called Global Event-Driven Architecture, or GEDA for short. And the way this looks in our single process, we have our nodes and one or more global event handlers. So now we just deployed a handful of threads to serve the whole cluster, matched with the total number of cores of the machine. So for example, now node 1, the blue one, used the global queue for its event, and the green one does the same. So they share. The main challenge in here is to identify the constraints of each event. Single-threaded events cannot be posted concurrently. Otherwise, we will break the processing semantics. So here, if the green event is serial and the node submits another one, we need to enforce that serial processing. Now, with this approach, we were able to collocate 512 nodes in a single machine, which is a really big jump. So now we want to see our framework in practice. And to test it, we took some bugs, like, for example, this one, HDFS 91A8. So in this scenario, the name node has an RPC queue that has a limited size, 1,000. And the name node used this to receive commands and requests, etc. So every now and then, data nodes send incremental block reports, or IBRs. And these are processed in serial. So when we receive another block report and we want to process it, we need to wait for the previous one. So now at the right, we run a real scale cluster, the black line. In here, the x-axis is the number of data nodes, and the y-axis is the maximum observed queue size, the bug symptom. And we see that with 32 data nodes, we won't keep the queue full. And the same happens for 64 or for 128. Now, when we reach 256, we see how the queue fills up. And when that happens, no other request can be served. Now, we reproduce this bug using our framework. And as you can see here in the purple line, this is just a single machine. And you can see our accuracy, right? So for now, we can say that our framework works pretty well, but that was not always the case. We had other cases, for example, like this one. This is the bug that we talked about in the introduction, the Cassandra decommission problem, or removing one node. So here, the x-axis is the number of nodes, and the y-axis is the number of flaps times 1,000. And as you can see in the black line, the symptom only appears at 256 nodes. So when we use our framework below that number in the purple line, it worked pretty well, as you can see. But for 256 nodes, our metrics are way off, and we observe this big gap of inaccuracy in our symptom. So why do we have this gap? So when trying to reproduce this in a single machine, we did not take into account the fact that in this scenario, all nodes are CPU intensive. And because of that contention, as I said, our metrics are way off. So to solve this, we came up with one more trick, and we call that processing illusion, or PIL. And in here, what we do is to replace CPU-intensive computation with sleep. Our intuition is that the the key to the computation is the execution time and the output rather than the intermediate processing. But as you can imagine, there are many, many challenges when doing something like this. For example, what pieces of code can be safely replaced by sleep? And by safely, I mean without affecting the processing semantics. So let me show you 2 examples. In the first, we have this code block, and there is a triple nested loop in here, depending on the size of the cluster. So this is CPU intensive. So now, if we look at the body, we have one I/O operation writing something, and we notice that this one is non-pertinent, meaning that it doesn't really affect the behavior of the protocol under test. These kind of code blocks are good candidates for PIL. Here, in the first block, we maintain the original behavior. And in the next one, we replace that intense computation with sleep. So now this is constant. Now, since we need to sleep, how long do we sleep? For cases like this one, we noticed that we could profile that time offline in a single machine. And that was enough to keep our framework accurate. But other blocks are far harder to replace. In here, we see the same kind of body, also O in cube, but now inside, there is a pertinent operation that affects processing semantics, for example, by modifying the cluster state. We can also replace these blocks, but we will need a little more. In here again, we start by keeping the original behavior, and now we inject our own PIL, but this one is a little different. This time, we don't need just the processing time, we also need the output. So what we do here is to memoize. And we try this both offline, like in a single machine, and online, as taking traces from a real scale cluster. And both approaches work pretty similarly, but memoizing in a single machine usually could reach days. So it's really, really long. So now, with this new collocation trick, we move from this previous inaccurate scenario to the accurate one that I showed in the orange line. With PIL, we reach up to 512 CPU-hungry nodes in an accurate fashion, so now we can expose this bug. And not only this one. If you remember from the intro, we had other cases where the main symptom was flapping, and with those, our framework works accurately too. So now let's finalize with the evaluations and conclusions. So, well, for details on our bug reproduction, you can go to our paper. We reproduced 10 known problems, and as I told you, as I'm going to show you now, we also found 4 new ones. So in this case, we use sFind to try to find new problems, and we took the latest version of Cassandra. And we found this guy again, apply state locally, which is someone that we have already seen, right? In our previous workloads, this guy was the culprit too. And in this case, in this new version, this guy is O in cube still. But they improved it a little, and now instead of being quadratic in I/O and log, they are just linear. So they did a little better this time, for example, according to our testing. Now they can work with 256 nodes pretty well, but still at 512 they hit the same bug symptom. So the problem is not really fixed. And we also find new ones in HDFS, for example, in the snapshot path or in the meta-save path. So now let's discuss a little about our collocation factors. As I told you, collocation factor means how many nodes can we collocate in a single machine maintaining accuracy, which is very, very important. So here, I had 3 workloads, right? On the left, I have decommission on Cassandra. On the middle, I have incremental block reports in HDFS. And on the right, I have Voldemort rebalance, which is similar to rebalance protocol in Cassandra. So now, if we only use naive packing, right, just deploy processes in a single machine, you can see that we achieve different results. We have higher collocation factor for HDFS, for example, and really low for Cassandra. Now, if we add to the equation our single process isolation, right, you can see that we scale up both Voldemort and HDFS, but not really Cassandra, again, right? So after that, we added our network stuff, those per node queues that I mentioned. And while for Voldemort, that gave us like 512 nodes, Cassandra only scaled up a little. Our next technique, GEDA, allowed us to scale completely HDFS, right? So after that, we will be able to test 512 nodes in a single machine. But again, Cassandra was still failing. So for that, we had to add our new technique, PIL, in order to be able to test 512 nodes in a single machine. Now, the point of this is basically that whenever, for each workload, you might use our tooling in an incremental fashion, because that incremental fashion, depending on the workload, will allow you to collocate as many nodes as you can in a single machine. Okay, so well, in its current state, our work has some limitations, which we plan to address in future work. So for example, we only focus on scale-dependent CPU processing time, right, like cluster size or the number of files. And in the future, we plan to explore other axes of scalability, like load and failure. For now, our colocation factor is limited by a single machine, and that is in a way on purpose, because this is akin to unit testing, right? But in the future, we will also explore how this works and behaves in multiple machines. Of course, we will have to address many bottlenecks, like network, but we are going to explore. Now, as I told you, in some cases, PIL might require real scale memoization, because otherwise it takes too long, right? So what are we doing now? It's exploring other CPU contention reduction techniques to replace PIL and to overcome this challenge. And finally, our framework is not completely black box, so we need to add more code. And when you add code, you add new maintenance costs. We argue that that cost is really, really low, 1% of the code base, but in the future, we intend to move for zero-effort emulation. So finally, we have presented an approach to test distributed systems in a single machine, and we try to highlight the need of these kind of approaches to easy in the way of the life of the software developers of these kind of systems. Now, if you have any questions, I'll be happy to answer.
So to get things started, you said you found four new bugs. It was
4.
So have you reported those, and have they been confirmed and fixes in the work?
Yes,
or?
with our collaborators at Cloudera, we have reported them the HDFS ones, and the Cassandra decommission, since they are rebuilding the whole gossip mechanism, they are not like taking new tickets on that. They are rebuilding the whole system.
So it was just 4 in Cassandra? Did you find any new bugs in any of the other systems, HDFS or Voldemort?
At least for this paper, we only look at Cassandra and HDFS, right? Voldemort doesn't really have many new versions, and this is for Java-based system for now. So.
Okay. All right. Well, let's thank the speaker one last time, and then.
Thank you.